Hi, in this video we give 3 problems in construction and architecture using the theory of curves. The extensive use of curved lines in architecture and engineering has been the origin of many problems that can be tackled with the mathematical tools of this course. In particular, in this video, we are going to give 3 of these problems, namely, the best supporting arc, the best freestanding arc, and the optimal shape of a beam. The solutions of these 3 problems will be given in the third module. We begin with the first of them, the best supporting arc. We look for an arc spanning a gap and supporting a weight above it that is uniformly and linearly distributed. The typical example of this situation is the arc of a bridge, and the weight it has to support is a road above it. We now make precise the conditions of this problem. First, we explain what a uniform and linear distribution of the weight is. That means that if 1 meter of the construction weighs m kilos, 2 meters of the construction will weigh 2m kilos, and in general, x meters will weigh mx kilos. This is a uniform construction. The weight of it grows linearly with respect to the distance. In particular, if the total length of the construction is big L, the total weight of it will be ml kilos. The arc, of course, has to transfer this weight to the ground. And what does best arc mean? We look for an arc such that the tension or supporting force carrying the weight of a construction is always tangent to the trace of the arc. Then, the weight is transferred along the curve in such a way that no transverse forces are present. If the force is not tangent to the trace of the arc, we can decompose it into the tangent and normal parts. In the example of the image, the dark green vector is decomposed in a light green vector and a black vector. That transversal vector, the black one, if it's not controlled, may put the construction under risk. Then the mathematical formulation of the problem is as follows. If we consider a part of the arc from the top to any point at distance x, then the tangent force can be decomposed into horizontal and vertical parts. The vertical part must be the weight of the construction above it, that is, mx, whereas the horizontal part is constant. We have to find the curve satisfying those properties. We will see the solution in one of the videos of the third module. The second problem, the best freestanding arc. This is a very similar problem. In this case, the arc just supports itself. It does not have any construction above it. Now, the weight is proportional to the length of the arc, that is, 1 meter of the length weighs m kilos. 2 meters will weigh 2m kilos. But the proportion is not with respect to the horizontal distance, but the length. And in general, L meters of the length will weigh ml kilos. In the image you have what the length means, is the length of the arc. Again, if we have an image of the arc from the top to a certain point, then the decomposition of the horizontal and vertical part of the tangent force give these equalities. First, the vertical part must be equal to m times the length of the arc, whereas the horizontal part is a constant. We have to find the curve satisfying those conditions. We will see the solution of this problem in a video of the third module. In the last problem, we studied the optimal shape of a beam. We have a beam made of a more or less elastic material. It is flexible, but we assume that the length of it, L, is constant. That is, we can curve and twist the beam, but we cannot shrink or enlarge it. Then we are given 2 ingredients, an initial point equipped with a direction and a final point equipped also with a direction. These directions are defined by vectors on the points. We assume that the distance between the points is less than L. The question is, what is the natural shape of the curve drawn by the beam under those initial and final conditions? The solution of this problem will be given in one of the videos of the third module.